Please welcome to the stage DARPA's Information Innovation Office Director, Dr. Kathleen Fisher.
I'd like to thank the speakers this morning for their thoughtful remarks. We invited them here to set the stage so that we were all on the same page with respect to the dire threat that we are facing and how we have to change business as usual. We've been using this slide for a while with the sharkberg. The sharkberg, the iceberg, the analogy represents the immense cyber technical debt that we have amassed. And this technical debt represents all those vulnerabilities that adversaries have been hearing about have been exploiting to present threat to our national security. But unlike the traditional icebergs that are kind of just passively waiting there, our adversaries are actively driving that iceberg towards us to represent that threat. And part of the challenge is we have this learned helplessness with respect to those vulnerabilities that have just, of course, we write software, and despite our best efforts and our best practices today, that software has vulnerabilities, and those adversaries are going to exploit those vulnerabilities, and we fix it up after those exploited. That fix-up might mean, patching the vulnerabilities, paying ransomware, offering, insurance policies to people whose data were exploited. It means our commercial IP is stolen, and our adversaries get to take advantage of that very, hard-won commercial IP, and that's just what's done. It means that the ATO process, which is a very, very time-consuming, extensive paperwork process that gets, it's a well-intentioned process when it was created, that gives us the authority to operate military systems, et cetera, locks in vulnerabilities. Right? It takes a super long time to produce that paperwork to give us approval to operate those systems. When we get that approval, we don't want to have to go through that process again. So if we then know, and we find out that there's a vulnerability in one of those systems, we're like, okay, well, we're just going to accept the risks. And we go ahead and keep using it. Even though we know it has a vulnerability, our adversaries might know it has a vulnerability, the system is exploitable. The whole point of the ATO is to not have exploitable vulnerabilities in our systems. But everybody's like, yep, okay, we're just going to go with that exploitable vulnerability, right? Because it's just going to take too long to go and fix it, and we don't have the budget to go and fix it because it wasn't allocated and it's going to take too long, so we're just going to leave that exploitable vulnerability in the system. And we haven't had a major hack that's had national security consequences, so it hasn't happened in the past, it's not going to happen in the future, right? Well, that's not really sound reasoning, right? An adversary that might be planning something in the future wouldn't do it in the past to give us warning and get us prepared in the future. So we can't really take the fact that there hasn't been a catastrophic cyber national security event in the past to give us the confidence that it won't happen again in the future. So the status quo has to change. If we didn't have any technology to solve the problem, well, that'd be like, okay, well, we can't do any better than that. That's just the way it is. But we actually do know how to do better. And that's what we're leading up to. Because all the morning is like, we have to do better because we can do better. We know how to do better. And that's using these formal methods-based approaches that the whole rest of the program will be focused on. The whole point of today wasn't to get you super depressed about the state of software, which is probably where you are right now, right? The point is, we actually do know how to do better. Formal methods technology can help us. Now, it's not a panacea. It's not going to solve all problems. But I talk about formal methods as kind of an analogy with security for physical security, for houses, for businesses, for military installations. Right now, our analogy with where we are with cybersecurity is our doors are open. Our windows are open. We actually know how to close the doors, close the windows, and lock the doors and lock the windows. And we are choosing not to use that technology. We are choosing to leave the doors open, leave the windows up, and not use the locks. So today is about talking about how to close the doors, close the windows, and lock the door, put the bolts closed, lock the windows, et cetera, to get to a much better state of security. And does that make the house impenetrable? Does that make the base impenetrable? No, a well-defended, well-resourced adversary can probably still break into our businesses, homes, military installations. But it will be a lot harder, and it will give us more time to defend ourselves, et cetera. So it's still a really good decision. Okay, so we've been talking a lot about formal methods. What the heck does formal methods mean? So formal methods is an umbrella term that means it covers a whole bunch of different kinds of technology. Often when I say formal methods, people assume that I'm talking about interactive theorem provers, things like Koch or Lean or Isabelle Hall, and they think I mean proving in those interactive theorem provers that the code that is under study is fully functionally correct. Sometimes that is what I'm talking about. That is a formal methods-based technology. That is pegged all the way to the right of very, very high level of effort, very, very high level of guarantee. Sometimes that's a perfectly appropriate, very appropriate technology to use. That's an appropriate technology to use if the software under question is the crown jewels, something where a very high level of effort, very high level of guarantee is perfectly appropriate. It's a level of effort that is appropriate if the software in question is going to be reused over and over and over and over and over, so that that level of effort is going to be a good return on investment. But there are many other kinds of formal methods too. Formal methods are simply mathematical-based approaches that will allow you to prove properties about your software to give you guarantees. Those guarantees are, the properties come with assumptions, right? Under certain assumptions, something is true about your code. The assumptions can be stronger or weaker. The guarantees can be stronger or weaker. The level of effort required to produce that proof can be lower or higher. Sometimes formal methods are completely in the background. If you've been using a type-safe language without escapes, so like Java without unsafe, you've been using a formal method. When you push compile and the type system comes back with, yep, you've proven property about your program, specifically that your program is type-safe, that every operation that your program will do when you execute the program respects a typing discipline. Like, for example, you are not going to add a function to an integer, because that's not a type-safe operation, right? That's a formal guarantee about the program. Similarly, if you use a high-level language that is memory safe, just by the virtue of using a memory-safe language, you have proven that your program is memory safe, which means that it will use all of the allocated bits in the raw seething mass of the memory of your program in a way that is consistent. You will allocate the memory before you use it. You will deallocate all of the memory, or the garbage collector actually will deallocate the memory in a time that is safe. Unlike C, where that guarantee of using the raw seething bits in the computer is not guaranteed. If you use Rust and you don't use the unsafe feature of Rust, then the type system of Rust will guarantee that you have used that raw seething bits of memory in Rust correctly. So Rust's type system guarantees memory safety. Those are also formal methods-based approaches. Those are on the lower level of effort. Type systems, memory systems, Rust a little bit further to the right, because the type system for Rust takes a little bit of getting used to. It's a little bit more complicated because the properties it's trying to prove are more complicated. Then we have things in the middle, like parser generators, which you're going to hear a lot more about in a little bit. Parsers are things that take data from off a system and take it into the system. So it's kind of like input validation. Parsers have very well-developed theory. They are an example of where you can describe the grammar, a high-level representation of what you're looking for, and automatically generate the low-level code for processing for actually processing the data, for processing what you want. And you can prove at the same time, you can produce a proof, the kind that the automated theorem prover would be able to generate, that the generated code, we check, that the generated code is correct. That's another whole class of formal methods-based approaches where you can specify at a very high level what you're talking about and reason at that very, very high level, and then generate the low-level code, sometimes generating a proof that that low-level code is correct. That kind of formal methods-based approach can actually be easier to use than just doing the low-level code yourself, because you can work at that very high level of abstraction. And you can not even know you're actually using a formal methods-based approach, because you're just coding at a level of abstraction that feels very natural, because the language is designed to mimic the problem that you're trying to solve. Then we have architecture analysis, where you can describe the architecture of the software, the system that you're building. And you can write that description and then prove properties about the overall architecture of the system because you're modeling the overall system. You can prove things like the only way to get a message from the radio to the flight control computer is through this one pathway. And every message that comes through that one pathway has to have been encrypted. It has to have been authenticated. And you can prove that way that there are no other side channels. Or when the proof fails, you can find out, oh, there was another side channel, and that we should close off that side channel. Or it was actually a rescue radio, and it's important that there's another side channel. But that side channel should also be encrypted and authenticated, for example. Then there's compartmentalization, which allows you to divide code into separate compartments and mediate the communication between those compartments. That's just a summary as you go across that dial of various kinds of formal methods-based approaches. Generally, the further you go to the right, the more level of effort it takes to use these technologies, but the stronger the level of guarantee you get from the use of these formal methods. Important aspects of formal methods is that they allow you to reason formally and have checked in some kind of automated way or some kind of machine-checked way properties like what can the system do, what will the system do, and perhaps most importantly, what can the system never do? So testing, right, which is a well tried and true thing in software engineering, can never tell you what the system will never do. You can never, ever, ever get enough test cases to exhaust the space, to get guarantees that the system will never do this. But with formal methods, you can get guarantees that under these assumptions, the system will never do this, which allows you to get confidence that an adversary will not be able to drive the system into certain bad cases. So when I talk about formal methods, sometimes people say, well, formal methods, that only works when you're talking about cyber-physical systems, or that only works when you're talking about distributed systems, or that only works when you're talking about fill in the blank. In fact, formal methods work when you're talking about any kind of software system or any kind of hardware system, right? They are very, very broadly applicable. They also sometimes say, well, it only works if you're talking about clean slate systems. I have a system that's already existing, so I'm off the hook. Like, no, formal methods work when you have existing code, and they work when you have a clean slate system. They work when you're tearing up the system and going to do a retrofit. They work at kind of all stages of the software lifecycle, which is good because we have lots of software at all stages of the software lifecycle. They generally work by employing models of the relevant parts of the system that you're interested in. So like the type system example gives an intuition for this. When you're, the model in that case is the abstraction of the value at the type level. So the abstraction is the type. So instead of thinking about, well, this is the number 3 or this is the number 10, it just thinks about this is an integer. Or instead of thinking about specific strings, it thinks about at the level of a string. Or in the architecture case, the model is like this is a radio, and this is a CPU, and this is a motor. Right? The level of abstraction in the architecture case is the components of the system, the architecture level. Right, then the proofs are generally expressed mathematically. This is when you get like the for alls and the exists. Often it's expressed in kind of logical notation. Sometimes it can be expressed graphically. Sometimes now it can be with large language models translated into human, more natural human representations in English, although you have to be careful because the reason it's usually expressed in logical representations is because it needs to be very, very precise. And human language is designed to be ambiguous, which is a problem if you're trying to do things precisely. And as I mentioned, sometimes it's behind the scenes, right? If you're using a type system, you didn't even probably know that you are all experts if you're coders in some formal languages because you all know how to program in a type-safe language, most likely. Yeah, and there, as I've been speaking about, there are many, many different kinds of formal languages, formal methods. There are many, many different kinds of formal methods tools. Right. Okay, so how did DARPA get involved in formal methods? It all started with the HACMS program in 2011, a very, very long time ago. And that's part of the point, right? DARPA is very much talking about getting formal methods adopted. And DARPA is still doing formal methods research, cutting edge over the horizon. We are not talking about trying to get the cutting edge tools adopted. We are trying to get the tools adopted that have been used for more than a decade. So HACMS. So the HACMS story got started with a quadcopter and Boeing's unmanned little bird, which is shown here. At the beginning of the program, a world-class red team was charged with trying to hack into the quadcopter and the Boeing unmanned little bird. Surprising to no one, they were able to wirelessly hack into the quadcopter and the Boeing unmanned little bird. Then the formal methods researchers got started on the quadcopter. 16 months, and they rewrote the software on the quadcopter. 16 months later, the red team tried again to hack into the quadcopter. This time, shocking to many, they were unable to hack into the quadcopter. That 16 months later, during that 16 months, they had followed what the formal methods researchers were doing. They saw the entire development process. They knew everything the formal methods researchers were doing. So it wasn't like they only had 6 weeks to try to hack in and take over control. They had the entire 16-month period to figure out how they were going to hack in. And despite that full knowledge, they were not able to do so. That same quadcopter, DARPA took it to the Aerospace Village at DEF CON in 2021. So 4 years ago, but many years after that work, and challenged all comers to hack in. Okay, break it now. No one was able to hack in. Even, 8 years later, it stood the test of time because the formal methods allowed them to architect and build code that was much, much harder to hack into. So after the formal methods engineers built the code for the quadcopter, it was about 80,000, 90,000 lines of code that they built in that 16 months of time. They then taught the Boeing aviation engineers how to apply the same tools and techniques to the Boeing unmanned little bird. Note, it was not the formal methods engineers who applied the technology to the Boeing unmanned little bird. The formal methods engineers couldn't do it because the Boeing unmanned little bird was ITAR restricted and proprietary. So only the Boeing aviation engineers were able to see the code base. So they applied the tools and techniques to the Boeing unmanned little bird. And then at the end of another 16 months, the red team was allowed to attack the Boeing unmanned little bird. This time, though, they didn't have to attack from off the system. They were allowed to put whatever code they wanted in a partition on the unmanned little bird. They were given root access to that partition on the Boeing unmanned little bird. And again, they were allowed to follow the entire development process. So they knew as much as you could possibly know about that unmanned little bird. They didn't have only 6 weeks to figure out what was going on. And they were charged with disrupting the operation of the helicopter. And they were not able to do so. All they could do was crash their own partition. They could basically fork bomb themselves. At the end of the program, they were charged with trying again. But this time, they were charged with doing it while the helicopter was in flight with 2 test pilots on board. Not only did the test pilots survive, which is good, they are test pilots, they're kind of crazy, right? The test pilots couldn't tell that they were flying the high assurance version of the helicopter instead of the version of the helicopter that they started with. The only thing they could tell was that the camera partition kept going down because the camera partition was the partition in which the red team was allowed to put whatever code they wanted. So when the red team got around to fork bombing their partition to see if they could disrupt the operation of the helicopter by crashing their own partition, they crashed the camera partition. The rest of the system was like, oh, the camera's gone down again, and would restart the camera partition, which would allow the camera partition to come up again. So how did that work? What was the magic behind the HACMS success? So the drawing on the left is the architecture description of the HACMS system. This was codified in the AADL language, the architecture analysis and design language, which was what the formal methods engineers and the Boeing aviation engineers used to reason about what parts of the system they needed to replace to get a high assurance system, and what parts of the system weren't really particularly important from a high assurance perspective. This was the language that they used to prove properties like the only path from the ground station to the mission control computer was through a pathway that guaranteed authentication and encryption so that you knew that only authenticated and authorized people were communicating to the helicopter. You can see the architecture. There's a flight control computer. There's a mission control computer. they used the SEL4 microkernel, which is one of these exquisite artifacts that was proven to be fully functionally correct in the Isabelle Hall theorem prover. That took 11 person-years of work to prove fully functionally correct. But that was proven fully functionally correct in like 2009, and is, sorry? 2009, thank you, Mike, and has been reused for 15 years, more than 15 years afterwards. So that level of effort for that kind of artifact has been well worth it. And that is the piece of software that provided the separation between the camera partition, which is the orange piece there, which is where the red team was allowed to put whatever code they wanted, and the flight control software that is what controlled the actual helicopter controls, and the part that communicated to the ground station, the part that communicated to the flight control computer. Basically, that is what we trusted the pilot's life with. So very, very high assurance software. And then we had verified parsers, which is what guaranteed that malformed messages would not be able to crash or take over control of the helicopter. You'll hear and see more about HACMS because we'll get a demo of the quadcopter later on from Darren Kofer, who is probably super, super sick of giving demos of the HACMS helicopter. He's like, but it's super old technology. And I'm like, yes, the point is it's super old technology. We are not asking people to adopt bleeding edge technology. We're asking people to adopt tried and true technology that is ready for widespread adoption. So, one organization that has adopted formal methods-based technology is Amazon Web Services. Byron Cook went to Amazon Web Services around 2011, actually, when was it? Do you remember? A little more than 10 years ago, so 2025, 15. And the way Byron tells it is that he felt like he had 1 year to demonstrate that formal methods technology would be relevant at Amazon. And so he looked at their list of critical projects, and he went through it and he found 5 projects where he felt formal methods could make a difference. And if one of them was successful, he figured he wouldn't get fired. Turns out all 5 of them were home runs. So not only did he not get fired, he's been super, super successful at Amazon. And he reports that they've been able to find places where formal methods are successful, not just for cybersecurity, but also for cost and performance and schedule. So kind of a program manager's dream, right? You get all of those. And now, why might that be? So they, at our request, they published a blog about one of these examples, which is the simple storage system, which isn't really simple. It's a database that stores objects, and there are something like 17 different processes that write and take out objects out of this simple storage system. And they had a bug in this system that they couldn't track down what the source of this bug was. Now, there was another process that fixed up the bug, so it was okay that the bug was there, but they really wanted to get rid of this bug, and it complicated improvements to the simple storage system. And every time they want, and the simple storage system has like more than 1 million updates a second, right? So it's a workhorse for Amazon Web Services. It's very important. But whenever they wanted to make changes, they have to deal with this bug and deal with the complexity of the system and how high performance it was. And so lots and lots of testing was involved. And because there's 17 different daemons that are making updates to the system, there's tons and tons and tons of different cases. And so testing is, the combinatorial explosion is enormous. So eventually they called in Byron and the formal methods team to try to prove it correct. And of course, there's a bug. You can't prove it correct. But the methodological, like the discipline of trying to prove it correct allowed them to find the bug and fix the bug. And now they have the discipline of whenever you want to make a change, you have to prove it correct. And that allows them to make changes much, much faster than the previous regime of doing a ton of testing with a combinatorial explosion of different cases. And that means they can make changes much faster than they could before in a way that is much more predictable with how much time it's going to take, which allows them to make optimizations much faster. So they get better performance, they get better predictability, they get better cost. And as a result of this decade of now commitment to formal methods, they have now formal methods throughout their code base, and that is underlying many code, all segments of their business, which is what all those red circles are. And don't just take it from me, Mike Hicks is going to be talking later on and talking about their experiences at Amazon Web Services. So DARPA didn't stop with HACMS. So this is a timeline of DARPA's investments in formal methods over the past 15 years. We see HACMS at the beginning. When DARPA invested in HACMS, like I found out like after the first quadcopter experiment that DARPA actually invested in HACMS thinking it would fail completely. So that's what DARPA does, right? Invest in stuff that they think is going to fail, high risk, high reward. But that after the quadcopter experiment, they realized, or they decided that the program was already a huge success. After the end of the HACMS program, they decided that HACMS was a huge success and started to explore in other kinds of formal methods. So the CASE program was about moving cyber requirements from the very, like the typical way of developing cyber would be you develop your whole system, you get to the very end of the development, and then you start testing for cyber kind of properties by red teaming kinds of things. And then you realize, ooh, my cyber's bad. And then you have to go back to the very beginning and start changing things that you would have wanted to have done much earlier in the process. So the CASE program was about, can we lift up and move much earlier in the process cyber kinds of requirements? And Ray Richards was the program manager for CASE, and he is sitting at the table right here at the beginning. So if you want to have more information about CASE, you can talk to Ray. SafeDocs is about parsing, and how do we have richer grammars for expressing the formats for our data formats for parsing, and then automatically generating parsers. And you can also get parsers where the generated parser code is proven to be functionally correct. ARCOS is about that authority to operate process. Instead of having it be completely paperwork and process-driven, can we have it be artifact-driven and checked using formal methods-based approaches? Ray was also the program manager for ARCOS. Oh, and Sergey is the program manager for SafeDocs. He's also sitting at that table. Then AMP was about, well, is it always source code? What if we only have the binary? What if we have binary, no source code, and we have a bug, and we need to fix that bug? Can we decompile that binary up to source code, and not just in a random way? Can we decompile the binary up to source code in a way that it matches our patch? Do the patch, and guarantee that when we recompile it back to the binary, the semantics won't have changed, that we will only have fixed the bug. Amazingly, the answer to that was like, yeah, that actually works. And that's one of the transitions that Rob mentioned earlier. vSpells then is about, what if we have massive, tons of like spaghetti, horrible code that we want to fix part of it? So like canonical examples are, you have like shotgun parser. So again, going back to parsers, but where it was written by hand, and you're interleaving the parsing with some of the processing of the data representation that is getting out, which is a anti-pattern. Like, you should never do that. And your organization has seen the light. You want to get rid of your shotgun parser and replace it with a beautiful generated, formally verified parser. But how do you identify where in that spaghetti code is your shotgun parser? Or you have, oh no, we have bad crypto, and we have quantum crypto, we have to upgrade our crypto. How do we identify where in our spaghetti code is the bad crypto to be able to rip out the bad crypto and replace it with quantum modernization crypto? So that's what vSpell is doing. And it also, when I heard about the concept behind vSpells, which is you can identify the abstractions, domain-specific language abstractions in spaghetti code, lift it up, and then replace it with a new abstraction and push it back down again, I thought, like, that's crazy. But in fact, we've also been demonstrating in vSpells that that idea works as well. Harden is about weird machines, where you have not just the abstractions that you anticipated when you were building a abstraction, but that you have other abstractions that were unintended, often that across abstraction layers, that adversaries are very good at finding and programming to get to do whatever they want to do instead of what you want to do. Harden is about identifying those cross-abstraction layer weird machines, kind of Turing machines that cross layers that allow adversaries to program that weird machine. Harden is about automatically identifying those cross-layer programmable machines and eliminating them. right? And then, so those are sort of the programs that are either finished or mostly finished. And then over the horizon are the next programs. These are not programs that we are hoping that you would start transitioning and using the technology, but we want to give you a glimpse over the horizon of what might be coming in the near future. So provers is about interactive theorem provers, and similar cutting edge, kind of more to the right of formal methods-based technology. Can we make those technologies much, much easier to use? Can we integrate that kind of interactive theorem prover technology into standard workflows to make it so that it is easy to use, that even if you don't have a PhD in formal methods, for example? And part of the hypothesis here is, like, you have artificial intelligence, which is very, very flexible, very, very easy to use technology, but not so good at being trusted. And then you have formal methods, which is very good at being trusted, not so easy to use. Can we put those two together? So can we instrument theorem proving technology with AI to make the theorem proving technology much easier to use and integrate it into normal workflows for normal developers? That's the hypothesis of provers, and it's producing some really interesting results so far. And Brad Martin was the program manager who started that, and he is sitting right over there. And then CPM is about compartmentalization. So one of the secret sauces of HACMS was the SEO4, which allowed us to compartmentalize the camera partition and the rest of the partitions and guarantee that, like, no matter what the red team did in the camera partition, it could not screw up the other partitions that were necessary for the correct functioning of the helicopter. CPM is taking that idea and putting it on steroids. Can we take a huge code base like the Linux kernel and automatically partition it into many, many small partitions so that if an adversary does break in, can that adversary be guaranteed to be held to to one partition and not corrupt the entire code base? And analysis shows that if we're able to do that, the vast majority of today's penetrations would not be successful at accomplishing what the adversary wants to accomplish. Then EBOS is about software bills of materials. The motivation for EBOS is the log4j vulnerability, where the vulnerability came out and we realized that there were millions and millions of sites that were vulnerable to that attack. Could we instrument software bills of materials so that they were tied to code bases so that we could take that vulnerability and find instantaneously, basically within minutes, all of the code bases that were vulnerable and all of the places where we could go patch the associated code to make it so that we were only exposed for minutes in the best case, not months, years, as we currently are. And Sergey was the program manager who started that, and he is still sitting over there. And then Tractor, right? So the lack of memory safety is a massive vulnerability. A very large number of our vulnerabilities would go away if we just got rid of memory in unsafe languages, so C and C++. The Tractor program the hypothesis is, could we leverage large language models paired with cyber reasoning systems to automatically translate from C into idiomatic Rust, so that we could translate trillions of lines of, in the long run, C, C++ into idiomatic Rust and get rid of C permanently. Right now, the first phase of the program is just looking at single-threaded C, so an important but just baby step to start. So like aviation code is written in just single-threaded C, so that would be an important first step. The second phase of the program goes to multi-threaded C, which there's a ton of multi-threaded C. If that's successful, we'll have to see about who would go tackle the C++ program. And then ICS is mixed reality use. So mixed reality headsets, there are attacks that would make somebody using mixed reality be distracted, be dizzy, be confused about their actual mission. Can we use formal methods to make it so that we could defend such people in advance of us actually seeing such attacks in a widespread use, using models of cognition and not just models of code? Okay, so that is pulling back the curtain of what's coming over the horizon, but not technology that we expect you to be adopting in the near term. Okay, moving forward. So, as Rob said earlier, The transition to 23 different relevant military systems, not good enough. We need to transition our formal methods portfolio to the entire defense industrial base, to the entire DoD, to the entire critical infrastructure. So we have a lot of work to do. So we started by convening roundtable discussions with the defense industrial base, by convening partnerships with R&E, with ANS, acquisition and sustainment, with DOT&E. We had roundtable in which we brought those two groups together. It was a very interesting conversation where some of the DIB partners were like, we're already using formal methods, we just can't get paid for it because it's not a requirement. We had another DIB prime say they know about formal methods, but they're not using it because they can't get paid for it. This is where there is a policy problem. Other formal methods companies like, formal methods, what exactly are formal methods? Can we pay somebody to use them for us? Oh, and by the way, are they like TRL level 9, shrink wrapped, perfectly ready to be used? And then we had ANS say, well, we can't require companies to use this technology because they don't know how to use it and that they would fail, right? So a little bit of a cross purposes. So we're trying to get a spiral going where we can get everybody on the same page and the same level of awareness that these technologies exist and are ready for prime time, and that there's a user base, a customer base that is ready to use these technologies. DARPA is moving forward with dogfooding this technology. So we are preparing to have our solicitations, if there's a software component, have another criteria for evaluation, which is a resilient software systems evaluation criteria. We put out a request for information on this in the late December timeframe or early spring timeframe. We've just evaluated all of those responses. I was pleasantly surprised that the overwhelming response was, this is a really good idea, what took you so long? So we will be moving out on that. So look forward to that in the near future. And then another piece of that is hosting this Resilient Software Systems Colloquium. One of the things that came out of the Defense Industrial Base Roundtable was we challenged each of the DIB companies to go back to their home institution, find a place where they had a system where they could use formal methods and try it out and come back and report on that, which they did 6 months later. One of the things they charged us with was, well, how much improvement do you get? What exactly are you doing, and how much does it cost? Right? We had the experience of HACMS, but that was a research experience, and we didn't record exactly. It wasn't sort of meaningful to record, well, exactly how much did it cost and how. And so what we did from that was we created a new program, which are these capstone demonstrations. We are partnering with each of the services on a capstone demonstration. Each of these capstone demonstrations are pick a platform or a part of a platform, do a red team assessment of its current state of cyber vulnerabilities, then do a formal methods retrofit, documenting what you're doing in a best practices guide. And there we're partnering with ANS. ANS is doing that documentation in a best practices guide. John Garska, who's on a panel later today, is leading that effort. And then after the retrofit, we're going to do another red team assessment to be able to diff what the best practices guide, what the retrofit produced in terms of the delta in cybersecurity. So the Air Force is leading the pack with the retrofit on the MQ-9 Reaper, and the other services are not far behind. So hopefully we'll be able to announce those very, very soon. One of the things also that came out of those DIB roundtables is Anduril came to the roundtable, and they have announced, or they're announcing today, that they are partnering with Riverside Research in doing their own pilot on updating their parser with the Hammer parser that you're going to see demoed later on one of their systems. And if that is successful, they are going to be rolling out that technology across a large swath of their product line. So super, super excited to hear that. Then that brings us to you and today. So the people here who are wearing the gold lanyards and the blue lanyards are people in industry and government who are responsible for systems, software systems that could benefit potentially from a cyber resilient systems formal methods upgrade. And it might, you're currently formal methods curious, or you wouldn't be here. But it might be that you think that it might be too hard, or that it might be impossible. Then you can, embodied as Alice from Through the Looking Glass. But we're here to help you with the White Queen from Through the Looking Glass, who has believed as many as 6 impossible things before breakfast, with the people who have the orange or the purple lanyards, who are experts in formal methods. And we are here to call you to action, to seize this opportunity, and to help you, motivate you to listen and to think about where you have systems at home that might benefit from formal methods. And to do the same thing that we did with the big 6 DIBs, where we challenged them to think about where you have software back in your home institution that might benefit from a formal methods retrofit, and where you might do that upgrade. DARPA is announcing today that we are going to do the same call for a capstone activity, where we're going to offer funding to do a red team, an assessment of a system. You guys do the cyber retrofit, and then do another red team to assess the difference. Document what you did in the retrofit in a best practices standard format. Either you can do that on your own, or you can partner with a formal methods company or academia who can provide that formal methods expertise. So part of what the goal is today is to socialize and to provide mixing. So the lanyards are to help people identify. So blue and gold are organizations that have code that might need the retrofit. Orange and purple are organizations that have formal methods expertise. The tables are intended to mix you guys up, so at lunch and during breaks you can talk to each other. There's a poster session with more than 50 posters of people who have formal methods expertise to provide, again, access to different kinds of formal methods technology that might be relevant to your particular problems and expertise, so that you can find technology that might be relevant to your particular problem. So the QR code that is here provides access to the special notice. It's also on the back of your program. So again, this is seed funding to provide defense industrial-based companies to partner with formal methods tool developers to apply formal methods tools, which are, again, any kind of formal methods tools that provide some kind of guarantee that will then document what you actually did in a best practices guide to measure the level of impact and the level of effort that was required in that partnership. Yeah. This QR code is available in the back of your program, and it will also be available at the end of the day. And so we encourage you to not just talk to your friends and not just stare at your shoes, as we're all good introverts and are inclined to stare at our shoes, me included, to talk to the people with the opposite kind of skill set and really start thinking about where you have systems that might benefit from these kind of formal methods, motivated by all the scary talk this morning about where we might be if we don't really start taking seriously this kind of technology that will allow us to significantly improve the cybersecurity of our systems by applying these formal methods-based technologies. And I didn't say this part, but this afternoon you will hear about program managers talking about the programs that I mentioned earlier in more detail about the formal methods-based technologies that we have used to demonstrate provably much harder to hack into systems. So lots and lots of resources, like the whole afternoon is about formal methods resources that you can use to produce systems that are much, much harder to hack into. I keep saying, I don't say not hackable because every system is hackable. It all depends on the threat model, but still much, much harder to hack into. We also want to hear from you, so there's 2 QR codes that are sort of relevant. So the one that I just showed you is for the special notice for the funding opportunity. This one is for you to give us feedback on the messaging that we're using about formal methods, right? There's a lot of I can't use formal methods because, or I don't understand about formal methods. We want to understand from you, what are your remaining confusions? Where do you have questions? What would make a difference to you about using formal methods? So you can fill this out now, or maybe more appropriately at the end of the day. Again, this QR code will be available at the end of the day. What's your feedback on what are your remaining questions? What are your remaining hangouts, so that we can do a better job messaging about formal methods? And I think the next thing is the networking break and the poster session. So hopefully you are now really, really motivated to network with people with the different color lanyards and to go to the poster session and find out more about what formal methods can do to help you and the code you're responsible for, and to make it so that we don't lose our next serious conflict because of the sorry state of our cyber technical debt. Thank you very much for your time and attention. I'll be available.